Okay, we can start. Good morning and welcome. Our speaker today is Luzzi. She is a planetary geologist with a focus on Mars and other bodies of a solar system. She earned her PhD in planetary science at the Construction University in Bremen. And during her PhD, she was involved in collaboration with the ESA astronauts and participation in several projects such as the Horizon 2020 Plan Map and the Europlanet GMAP. She is currently work at the University of Mississippi, and she's investigating brine pools in the Gulf of Mexico as terrestrial analogs for Enceladus. And now she's studying near surface ice on Mars in support to in situ resources utilization strategies. She is an author of 20 scientific publications. So please, I leave you.
Yeah. Good morning, everyone. Today we're going to talk about a very exciting project at NASA that I was very lucky to be part of during my first postdoc. And in particular, our work focused on geomorphological characterization of 3 candidate landing sites on Mars in the northern mid-latitudes. And what we were looking for was near surface ice in particular, because these candidate landing sites were specifically selected for future human exploration. And so we need water, so therefore we need water ice. Now, before delving into the geomorphology, and by the way, I'm not going too much into detail with the geology because I know we have a diverse audience, so we will talk about other things too. But before going into detail with the geology, let's take a few steps back and talk about the human dream of a human settlement on Mars. Maybe. It was working until now. It's just working. Okay. Yes, okay. So humans have been explorers for thousands of years now. We started with our planet, of course, and humans have always been driven by curiosity and wanting to overcome challenges and the discovery. But now we are moving on to other planets as the technology advances, and human settlements on Mars are considered possible by several space agencies like NASA, ESA, and Roscosmos. But they're not considered a priority yet, and that's because there are many risks, the costs are very high. So while human exploration is conceived as possible, it's just not a priority in the near future. The first 2 people to propose to colonize Mars were the pioneers Robert Zubrin and David Baker in 1990. They later also formed the Mars Society that now has a famous member, Elon Musk, that basically aims to build a colony on Mars. But in 1990, we didn't have the technology yet, and the costs were too high. And so this dream just didn't happen. This proposal didn't turn into reality. And then in 2017, at the World Government Summit, the United Arab Emirates also announced a plan on their own to establish a human settlement on Mars by 2117. So it's a pretty realistic estimate. But there's someone else who has been a bit less realistic, but who's actually the closest to reach this goal, and that is SpaceX. SpaceX in 2011 first proposed the Red Dragon mission with these landers. This is an artist's concept that you can see in this image of the Red Dragon landers who would bring this human colony to Mars. But then with new technologic advancement, with the Starship spacecraft, the focus shifted to the Starship. This is a picture of the Starship. The Starship is just an extraordinary advancement. It's like nothing we've ever seen before. For all these reasons, first of all, the payload, it's an incredible amount of payload, 150 metric tons, compared to the 140 of Saturn V, which is the last huge technology advancement in rocket science. And Saturn V did bring humans to the moon in the 70s, so it was huge. But in the last 50 years, there has never been technology advancement as big as this one. So Starship is a complete game changer. Most of all because it's fully reusable. For the first time, we do not throw a rocket just after one use, but we're able to land the rocket and start again. So if you imagine using a vehicle just once, like an airplane, for instance, you go somewhere and then you throw the airplane away, you just use it once. That's such a waste of money, the materials, and so on. And not just because it's a waste, but also because it allows to, it enables missions like sample return missions and human missions, since you can actually go back after you arrive there. One big problem, one issue to go to Mars was the propellant, because we know that just to exit Earth's gravity, a lot of propellant is used. And so Starship has a very incredible system where it can dock with another Starship, a tanker, which is just full of propellant. And they dock in terrestrial orbit. So the first Starship leaves the Earth, goes into terrestrial orbit and meets the tanker, refill the propellants, and then it's a fresh start for a journey to Mars. This is something that, for instance, Saturn V did not allow. And then it's also going to be very, very cheap. For instance, the Perseverance mission, the launch cost was $243 million, which is $100,000 per pound of payload. What Starship is aiming to do is to launch just for $2 million, which is $900 per pound. You can see the difference is incredible. And this will allow space exploration to be cheaper, but also more common. And we will have many more scientific missions since the cost will be decreased that much. These are two artist concepts of the colonization of Mars with the Starship. The payload that the Starship can bring will allow to have heavy construction machinery, and so you can build whatever you need for in situ resource utilization, but also as living spaces. Also, SpaceX is working with a company who creates these prefabricated living modules. And they're able to build cities in the desert out of nowhere in just a few hours. And Starship can actually bring these modules on Mars. And just in a few hours, you can develop a settlement. And also it can bring other drills or other instruments that are needed for science, for resource utilization, supplies, and whatnot. So now we talked about the Starship a bit, but let's talk about the candidate landing sites, because for such an important mission, there are a lot of criteria that need to be met for the candidate landing sites. The first two things that we're gonna look at are science and human exploration. So we want an area that is scientifically important, that can answer many scientific questions, like, for example, on the past climate of Mars, on the astrobiology, the geology. And at the same time, this area has to support human exploration. And so we need resources that we can use. We cannot rely on Earth going back and forth. Water ice is critical to do that, not just because humans drink water, but we also need oxygen, we need hydrogen for propellant production. And so having an area rich in near surface, accessible water ice is crucial. But these are not the only two things that we need. We also need a benign thermal environment for engineering. We cannot go to the poles because it would be too cold. And at the same time, we need solar illumination. We need insulation for power and operations. So these two things would drive us toward lower latitude. to the equator. But then at the equator, we would have the issue of not having accessible near surface ice since it's not stable. And so we need to find the sweet spot between the low latitudes and the high latitudes where we do have ice, but we also have solar illumination and a benign thermal environment. And these that we just described were the engineering and human exploration conditions that need to be met. But then there's also the safety of the landing site. So we have additional criteria that need to be met. For instance, the elevation, usually -3 kilometers with respect to the molecular is the preferred elevation. And that is simply because there is more atmosphere to slow down the descent. And then the slopes, of course, have to be gentle, not more than 5 degrees over a 10-meter length scale. And we don't want a high chance of impacting rocks that are bigger than a meter in diameter. Of course, the surface of the landing site should be radar reflective because we want to measure the distance as we descend. And the landing site should also be load bearing. So we don't want an area where you have the lava tubes or possible caves that would not support the landing. In 2021, Golombek et al. Selected a few canyon landing sites that were actually meeting these criteria. They were in the northern mid-latitudes. A group of these landing sites were in Flegramontes, a group was in Erebus Montes, and then Arcadia Planitia. And it's not actually Arcadia Planitia, it's Northern Amazones, but for some reason they called it Arcadia. So, but just to avoid confusion, we would call it AP, which stands both for Arcadia and Amazones. So we decided to start with analyzing the Arcadia Planitia sites because they were located in areas that were very flat and therefore safe for landing. They were at the mid-latitude, so there was good chances of having near-surface ice, and there was actually evidence for near-surface ice in data sets and in the literature. So we already knew that those were going to be very good. Among all the canyon landing sites that they proposed, we decided to go with these three. Apparently, they had the highest potential for subsurface ice, according to the authors. And also, the areas are so flat that we knew it would be a safe landing. Now, before going into the geomorphology of this area, a little ice glossary for those of you who are not familiar with this. So first of all, permafrost. We refer to permafrost when we have a perennially frozen ground with a temperature always below 0. Permafrost doesn't necessarily have ice, but most of the time it does. And when it does, the ice can occur in different forms. The two that we're more interested into, which are also the most common, are pore ice and excess ice. Pore ice, as the name suggests, is just ice that fills the pores within a matrix, while excess ice is the volume of ice in the ground that exceeds the total pore volume that the ground would have if not frozen. So of course, here also on the right, you can see the difference between pore ice and excess ice. Excess ice is purer, it's pure. So of course, for extraction purposes, we would prefer that. One big question is how this excess ice, how was it deposited on Mars? Since we know that with the current conditions, ice is not stable on the surface, especially at the low and middle latitudes. Well, during periods of high obliquity in the past, ice was actually stable at these latitudes, and it was being redeposited, transported from the poles to the lower and middle latitudes through snowfalls. And then this snow was compacted, buried, and we have these thick deposits of ice that are believed to be abundant in the northern middle latitudes. And then after this snowfall becomes ice and becomes buried by a dry lag, it is shielded from sublimation because right now, as I said, ice is not stable, and so it would sublimate right away. This dry lag, luckily, tends to shield this ice and protect it. There are multiple lines of evidence suggesting that Arcadia Planitia is rich of exercise. They come from the neutron spectrometers, both Mons and Friend, for instance. They found water equivalent hydrogen, high percentages of water equivalent hydrogen in Arcadia. And then also radar data. Brownson et al. In 2015 found thick deposits of exercise in Arcadia Planitia. And then we also have other types of data. We have imagery, and lots of geomorphological studies suggest that Arcadia Planitia is rich not only in ice, but exercise particularly. And then the SWIM team combined all of these data sets and came up with ice consistency maps that we will see later more in detail. One of the works that announced the presence of exercise in Arcadia Planitia before we started to investigate is this one from Hibbert et al. In 2021. They mapped what they believe to be a pure ice stream, which is this purple deposit. It's huge. You can see the scale. It's 100 kilometers. It's a huge pure ice deposit that is buried, according to the authors, and it's right on top, well, below, actually, our Candian landing sites. So there was evidence already, and when we started to look at the images, we found consistency with this. The most common geomorphological feature was polygonal pattern ground that we interpreted as thermal contraction polygons. Thermal contraction polygons are formed due to seasonal changes of temperature. So we have a decrease in temperature, the tensile stress exceeds the strength of the frozen ground, and this stress is relieved through the formation of these honeycomb networks of fractures, and the stress is released. And then season by season, these polygons tend to keep evolving. The cracks are usually filled by either ice or sand. To be filled with ice, you need freeze-thaw cycles because they're first filled by water, and then this water freezes and it becomes an ice wedge. Or in the case of a very dry, cold but dry environment, you can have sand wedges. So these cracks are filled by sand. Polygons can give us a lot of information. For instance, their size is related to the ice depth. So we know that smaller polygons correspond to a shallower ice table and vice versa. And they can also tell us about the maturity stage of the system because right angles correspond to younger system. Larger angles correspond to more mature systems. So by analyzing these polygons, we can actually extract quite a few information. A particular type of sand wedge polygon that you can see here on the right is called sublimation polygon or peak-top polygon here in this image. These sand wedges polygons have been extremely modified by sublimation, continued sublimation, especially at the sand wedges where the porosity tends to protect less the buried ice. You have more sublimation, and so the troughs tend to deepen and deepen and deepen, and the center tends to be almost like a mound, almost like a knob if you look at that. If you look at these. So these are very high centered polygons in areas where you have evidence of sublimation. In addition to the polygons, we will see there are also other features suggesting sublimation. And so we interpreted the polygons in our Candian landing sites to be sublimation polygons. Of course, just based on remote sensing, you cannot certainly say what type of polygons these are. You need ground truth, but you can have your best guess, let's say. This is a cross-section and our interpretation of the sand wedges that are below our polygons. You can see they're very high center. Some of them are even looking like knobs. These types of polygons on Earth occur in, as I said before, dry environments, cold and dry environments like in Antarctica that have been found in Antarctica. And they are also proxy for exercise. Oops. Another feature are the expanded craters. These impact craters have been, again, degraded by sublimation. They've been studied for the first time by Viola et al. In 2015. And they almost don't look like craters. They're so degraded. The only preserved part of the crater is the north-facing scarp, and that is because it's less prone to ice ablation because it has less insulation. These craters are also only occurring when you have excess ice below. So this is additional evidence that this area is rich in excess ice and is subject to very strong sublimation. The arcuate ridges remain a bit enigmatic. They could be due to a couple of things. One is they could be the formed ridges of a glacial flow. We saw earlier that Hibbert et al. Interpreted this area to be a huge glacial flow. And so this would be consistent with glacial flow, the formed ridges. But then at the same time, they could also be due to differential sublimation, just because the terrain could have had some irregularities in the topography, and then the different orientation and insulation might have caused differential sublimation, and this self-organization in this specific north-western orientation. This is a cross-section, so you can see they're asymmetric. And then another feature that is also associated with intense sublimation is the brain terrain. The brain terrain is made of this anastomosing pattern of ridges and troughs. It does look like a brain, that's why it's called brain terrain. Recently, Hibbert et al. In 2022 proposed a terrestrial analog for the brain terrain. We were lacking a direct terrestrial analog. There have been some attempts in the literature, but this is the one that seems to resemble most the brain terrain. And it's the vermicular ridge features that the authors attribute to intense ablation of the buried ice. The brain terrain can occur in two different forms, open cell and closed cell brain terrain. The open cell is characterized by narrow ridges that are positive relief, and they delimit the pressed cells that have a flat floor. Closed cell brain terrain consists instead, it's the opposite. It's elevated cells delimited by broad troughs. And these two types of brain terrain can be in transitional contact or in sharp contact. Here you can see an example of sharp contact. Oh, this is between polygons and brain terrain. But you can see also here the transitional contact between the open cell and the closed cell. Here again, transitional contact between polygons and open cell, and transitional contact between polygons and closed cell. These three terrains, the polygonal terrain, the open cell, and closed cell brain terrain, seem always to be in contact with transitional contacts, less frequently with sharp contacts. And so that questions also their origin. Might it be related? Might it be that the brain terrain is actually an evolution of polygons? We don't have an answer about this yet. And then the most striking piece of evidence that can be considered ground truth is the ice exposing impact craters. These impact craters, they're recent and they excavated directly into ice. So we know for sure that there's ice there where they did excavate into ice, but some of them did not. You can see from this map, some are green, and that means that they are ice exposing impact crater. The red ones did not excavate into ice, and the yellow possibly. So this suggests that the ice table might be patchy. Maybe the depth of the ice table is not homogeneous. Maybe there's no ice at all where it didn't excavate ice. So although this area seems to be rich in excess ice, we need to be careful because some of these craters are not exposing ice. And so there is an heterogeneity that we still need to constrain. One of the ice exposing impact craters, this one, is very close to the candidate landing sites. It's adjacent to one of the candidate landing sites. It's called AP1. Yes, okay. And it's this one. The blue deposit that you can see here, it's the exposed ice. And it's so shallow, it's just 50, 60 centimeters from the surface. Now here, of course, it was monitored, and just in a few years, from 2015 to 2019, the ice almost completely sublimated. So that also confirms the intense sublimation that's operating in the area. But what's important is that the ice is there and it's super shallow, so it's accessible. And then this is a bonus, but we don't know if there are pingos on Mars because we need ground truth. So pingos are ice core mounts, but you need liquid water for pingos to form because this pressurized water is injected into the pingo. And we know that liquid water is not stable on Mars. So even though the aspect ratio is similar and they might be, we just cannot say for sure until we have ground truth. And this is it. Then with these geomorphological features, we built 3 maps that will serve as exploration package. And as you can see here, the blue and the green are 2 different types of polygonal pattern ground. One is called smooth and one is called knobby because it's particularly high centered. And you can see that the vast majority of these terrains is occupied by polygonal terrain, followed by expanded craters, and there are also many, many arcuate ridges. This table summarizes what types of features are at each candidate landing site, and if we should choose one of the 3 sites just based on the variety of geomorphological ice-related features, we would choose AP1 because all of them are occurring in these candidate landing sites, which is here. Okay, so now we saw that there is a good chance of ice being there, also a lot of ice because the region is vast. But how deep is this ice? The only indication we know, the only ground truth we have is that ice exposed in impact crater that exposed the ice at 50, 60 centimeters from the surface. But the region is huge, and how can we know more about the ice depth? Okay. So I mentioned earlier that the size of the polygons is directly related to the ice depth. So what we did was we mapped a lot of polygons, like 10,000 polygons in the region. Usually we had a sample area that was larger, close to the landing sites, and then random other sample areas, smaller. We mapped all of these polygons, and then we measured the diameter to try and see if there was a trend. And we have this very neat normal distribution here. The 3 sites all showed similar results. This is AP1, and we have a diameter of approximately 11 meters. And then in AP8 is 12 meters. In AP9, again, 11 meters. So it's quite consistent. This is a very large area. What can we do with this information? In 2014, Mellon et al. Came up with a numerical model that could predict the ice depth based on the size of the polygons. And they did so in Antarctica, where they went on the field, so they had ground truth. And they saw that for a polygon diameter of 10 meters, the ice depth was approximately 10 centimeters. And then we have also a similar piece of information for the Phoenix landing sites, where we have a lander, so again, ground truth. And we know that for polygons with a diameter between 3 and 5 meters, the ice depth was 6 centimeters. And for polygon diameter of 15 meters, the ice depth was 10 centimeters. So how do we come up with these numbers? We didn't have the time and the fundings also to perform the same numerical model that Mellon performed. That would have taken into account the rheology of the terrain, all the characteristics, the climate, but we couldn't do that. So how can we leverage the data we have without spending so much time on that numerical model? We just cross-referenced the two data sets. So this is Phoenix. We know that for polygons that are more or less 4 meters in diameter, the ice depth is 6 centimeters. For 15 meters of diameter, the ice depth is 10 centimeters. And then we have this blue curve that is for Antarctica. And if we cross our diameter of 11 meters with these two curves, we have this range. And of course, we would expect it to be more similar to Phoenix because it's the same planet than Antarctica, which is on Earth. So the first part of this range is the expected range for the ice depth of Arcadia Planitia, and the second part is possible, but it's not what we expect. So we expect something between 8 and 10 centimeters of ice depth during the time when the polygons were formed. Now, the geological evidence says that there is ice. We also have the ice exposed in impact crater, which is really neat, but the models do not predict ice to be here. These are the SWIM models. I mentioned earlier that the SWIM team combined all the data sets and came up with an ice consistency map. It is a global map, and the maximum value is 1. So 0 means no ice, it's not consistent with ice, and 1 means there is a high ice consistency. And we can see that our canyon landing sites, the values are very low. Here, they're even 0. At the ice exposed in impact crater, also we have a couple of zeros, very low values, but then the crater is there and it's exposing ice. And so this discrepancy must be due maybe to a difference of scale. These models are thought to be global, and we cannot apply them for localized studies such as this. And so maybe we need more models that can be applied to this type of scale. To conclude, the 3 canyon landing sites that we analyzed met all the conditions that we were looking for. They have a good solar insolation. They're located at the mid-latitude, so benign thermal environment. We have resources because near surface ice is there, it's accessible, and it's a very flat area, so it's safe for landing. There are no big rocks that can be impacted and so on. The geomorphology suggests that not only near surface ice is there, but that this ice is even excess ice, which is even better for resource utilization. And then as for the depth, we know that at the time of formation of the polygons, the depth should have been something like 10 centimeters. Today, of course, the ice table must be deeper because of sublimation. We found that the ice exposed in impact crater, that the ice was 50, 60 centimeters deep. But still, this is very accessible and easy to reach. And this is it. Thank you.
Thanks, Erika. So if you have a question for people online, if you have a question, you can write in the chat or you can raise your hand.
Nice presentation. I wanted to ask, do you know if some people already consider, for instance, Hellas Basin like a place where you do this kind of studies? No, Hellas Basin is like the big basin, like acting like a Planitia, but in the middle of the southern islands, where in fact, where maybe in the past it has also like a sea or an ocean in the before. You have a lot of clays in the margins. You may have some sulfates at some places there. So maybe this water that was possibly present in the past in this place, maybe the water is already is always trapped in the surface as ice. So I don't know if you will.
I didn't catch the name of the area that you said.
Hellas Basin.
Oh, Hellas. Yeah. Is it in the southern?
Yeah.
hemisphere? I never went there.
Okay.
But I think they're more focused on the northern mid-latitudes, just because they're right now they're constraining the ice better in the northern mid-latitudes.
Yeah, and just to ask like this, this global map from Vincent Don that shows where the ice were like reach, let's say. But I don't know if Elas basin is individual.
I may add that the point for Elas that it's so deep and it's a trouble for the dust. So
So
it may not be so safe.
okay. So there is more likely to reach during
And the idea is also that the dust storms, global dust storm,
Okay.
there is an hypothesis that it starts from Elas, then they expand. They can-
Yeah, no. I didn't know that. Something, thank you.
If you can go back to the slides when you are showing the detection of the small craters with ice. And you were using red for no ice and green for ice.
Oh, yeah.
and then yellow for. Because I was wondering whether it is the presence or not of the ice could be related to the freshness of these small
The
craters.
craters, they're all recent.
So
So they're all formed since the high rise was orbiting.
yeah,
was
but
operating.
how recent they are depends on each other, because you have shown that the when they form in another slide, you have shown that there is an evolution of this. So I was wondering whether the red one would be the last
Mhm.
the last
Stage.
stage of what you have shown.
Well, it could be, it could be. This is also a
Because
matter.
the time frame is something like 5 years.
Yeah,
2 years.
yeah. It's a matter of monitoring. Actually, now we're working on the follow-up paper in Plegramonte, so the other sites. And there is an ice exposing impact crater that was formed in 2006, but the first high-res image is 2008. So it's thought to be formed between 2006 and 2008. So it could be that these were formed earlier and we just realized it too late and the ice was already gone. Could be. But these are from these two works, Dandas et al. 2021 and Obar et al. 2022. We didn't map these, so I can't say for sure. I don't recall this topic being treated in the papers, but it could be.
But is there a program because I know that now with this trouble with NASA, ARISE was switched. The operation of ARISE were stopped. But do you know if there is a program to monitor this process with ARISE?
There was before the instrument broke. I don't know how is it going to happen in the future, but for now there is a monitoring program. So at these sites, usually there are like 10 high-res images that have been taken each year, sometimes even twice in a year. So, but yeah, I don't know how the future will look like.
Last question from my side, and do you know if CASISA has the potentiality to perform the same studies?
I think it does, yeah. Personally, I've never been able to access the CASIS data. Once I tried to ask for permission access, but I never got a reply, so.
I don't know if the gases cover this the northern plains, but
Yeah, it could be. Yeah, well, I didn't really insist on it. I just sent a request and it didn't happen, but I'm sure if I insist, then send an email, maybe they will.
Thank you.
But yeah, of course it could.
We have a question. So the question by Paulina is it possible that polygons are formed from CO2 ice? Is it possible to discriminate water ice from CO2 ice?
Well, it's possible if it's on the surface. If it's buried, there's no way to discriminate because we don't have, well, you can do it with radar maybe, but this is so shallow. It's near surface that Sharad, for instance, wouldn't get to such shallow depths. So there is not a way to discriminate, but I don't think, I've never heard of polygons formed above CO2 ice, so. This is a tricky question, actually. It's not a stupid question, that tricked me. But I'd say that I don't think so. That's my.
Other questions?
We have seen that it's a good path to the landing site because there is water around it, so there's also good engineering constraints, but is there any place where the future human can still from the radiation? Because that's also important.
Yeah, well, so these canyon landing sites are specifically linked with SpaceX because it's a collaboration between NASA and SpaceX. And what SpaceX is aiming to do is to build these prefabricated modules that I showed before, and they are supposed to protect for everything. Now, I don't know how they're doing on that side because I'm not an engineer, I don't work for them, but that's their plan.
Is there a, in CO2 ice, does it make you blood? Or features the same as water ice?
Again?
I just was thinking about the question online, she said, can you differentiate between water ice and CO2 ice? And then it said, never heard the GMOR, the polygon, for example, with CO2 ice. But, what do you?
Yeah, right, that's a good question. I don't know, probably, yeah.
Maybe.
I just, I've never seen it on Earth, and so I.
And actually, I know it's not your specific word, but the terrain, the example that you showed was like the terrain was associated with like a great band or a peak ring. Is the brain, I don't know, but just the question. Is the terrains only associated with?
No, well, what are you referring to? Let me see.
They can be, they're ever.
Yeah, actually. No, I think it was earlier. So in this case, I found it, this is close to AP8, one of the canyon landing sites. And within the terrace of this crater, I found brain terrain, but it's not just here, there's also a plain close to AP1 and other canyon landing sites. Why? Yeah, so here we are outside of this is not a crater, it's a plain, and there is brain terrain here as well and here as well. So this is just a particular case close to APA. There is this crater, and on a terrace there is brain terrain, but it's just a case.
And one other question about the ridges. I know it's not your,
The Arkwell ridges, yeah.
but
But actually, if you have suggestions on this, I would take it.
how do they know the direction? If they're from like a glacier movement.
Yeah, the glacial flow that was mapped by Hibbert et al. Was actually, according to them, moving in this direction. So it would make sense on that regard.
Just so it's moving to just because of it's moving to the north because it's colder to the north.
No, because they analyzed a huge area and the geomorphology of this incredibly huge area. We just analyzed an IRIS image here, an IRIS here, an IRIS here. They performed another type of work, it's another scale, and they finally interpreted it as an ice flow, but not based on the Arkwell ridges.
But so, okay.
Not all.
Yeah, definitely glacial and not like faults.
There could be, but we don't see any displacement. We don't see. I don't know. Would you think it's a compressive fault?
I just was wondering like how do they really know that that's a form of glacier?
I guess just for consistency with the whole other assemblage of features that are in the area. They're all ice related, either glacial or glacial.
But they could be, those other glacial things could be imprinted on the existing.
Yeah, yeah, for sure.
And I promise the last thing, I know everything is straight on latitudes. Because that's where the ice can be stable, but I know that Dundas, there's like a famous Dundas paper from maybe like 2018.
Mhm.
And they found ice like at the equator or just south, like it was.
I think it was around 20 something. It was not at the equator, but still low latitude.
There is still the chance you could make a landing site more to the south.
Yeah, I think yes, because we showed that models actually don't fit with the evidence. And so it could be that these high stability models are missing something. There is a chance. Yeah, also the water equivalent hydrogen is pretty high in different parts of the equator or low latitudes. So it's possible, it's just we haven't constrained it well yet. That would be a good idea.
Other question? So we don't have other question online. So thanks for attending.
Thanks.